right, we're beginning Chapter 2, and Chapter 2 is the beginning of real geometry, where we really start writing, learning how to write proofs, and really start formulating our thoughts, looking for patterns. And we start out kind of slow, and we start out with what we call inductive reasoning. And inductive reasoning is a type of reasoning that doctors use. We kind of call this the doctor's method. All right, so to get started, we're going to start out with some vocabulary words. A conjecture. A conjecture is an unproven statement based on observations. An unproven statement based on observations. So, and if you think about that, a doctor, when they're examining a patient, they're basing their conclusion on an illness on just maybe by some of the symptoms. They haven't run any tests or anything like that. Inductive reasoning is finding a pattern. You're finding a pattern in specific cases, and then you conclude with a conjecture for the general case. Now, this is what we call the doctor's method. Okay? Kind of helps you remember what the definition is. So finding a pattern in specific cases and then concluding with a conjecture. In other words, an unproven statement based on your observations. Now, a counterexample. A counterexample is a specific case for which a conjecture is false. So if you can find a counterexample for any of your patterns, if you think you found a pattern but you can find a specific case to prove it false, then that conjecture, then you can't say that this is true anymore. If you can find one counterexample, then you can't say that a case is true. You have to say that it is false. Okay, so down here, example 1, it says the table shows the number of sides and diagonals in certain polygons. Remember, polygons is many-sided figure. Based on the table, how many diagonals should a 9-sided convex polygon have? We're going to use the pattern to make a conjecture. So looking here, we have a triangle. A triangle has 3 sides and no diagonals. No diagonals because all the angles are connected, so we can't draw a diagonal from one angle to another. If you have a 4-sided figure or a quadrilateral, we can create 2 diagonals. 5-sided figure, a pentagon, we can create 5 diagonals. If we have a hexagon, a 6-sided figure, we can draw in 9 diagonals. And now this is where we start looking for the pattern. Every time we increase the number of sides of the polygon by 1 extra side, we get bigger by 1, we increase the increase of diagonals by 1 more. You started out with 0. If you increase by 1 side, you get 2 diagonals. You increase by 1 more side, you get 3 more diagonals, from 2 to 5. We increase by 1 side, now we've got 4 more diagonals. So we add this increase to the previous number. 2 plus 0 is 2. 3 plus 2 is 5. 4 plus 5 is 9. That's your pattern. So to write that out verbally, for every increase of a side, the number of diagonals increases by adding 1 to the previous change in diagonals. It's kind of confusing just to read that, but when you look at the picture over here, it tends to make more sense. So we add 1 to the increase of diagonals and add that increase amount to the previous number of diagonals to get the new number of diagonals. Okay. Okay, now then, in example 2, it says describe the pattern in numbers. Write the next number in the pattern. So right here, we have -1, -4, -16, -64. So if we go through, you could say, well, this one got smaller by 3, but this one got smaller by 12. This one got smaller by 48. Okay, so we're not adding anything to them or subtracting anything from them, but they are all multiples of 4. So if we multiplied 4 to each number, we get the next number. So we're increasing the pattern. So notice that each number in the pattern is 4 times the previous number. So the next 4 numbers, -64 times 4 would be a -256. -256 times 4 would get us a -1024. A -1024 times 4 gives us a -4096. So there's your pattern. Now then, to practice that, let's look at the next set, part A. All right, if we look here, we see that from 4 to 6 is an increase, and it's an increase of 2. I just start making up things, just whatever I notice about it, and it may not work in that pattern, but it leads me to what will work. So you just got to start with something. The next number is 3 more than the previous. The next number is 4 more than the previous. The next number is 5 more than the previous. So we're increasing the amount the next number is increasing by 1. So the next number should increase by 6. 18 plus 6 is 24. The next number should increase by 7. 24 plus 7 is 31. The next number should be 8 more. So then we would get 39. So those would be the next 3 numbers in the pattern. Part B, to go from -7 to -21. That's quite a jump. And if you can see the jump is getting bigger and bigger, usually that indicates multiplication. So if I multiply -7 times 3, I would get a -21. And if I were to multiply -21 times 3, I would get a -63. And I just keep going with that pattern. So I multiply -189 times 3, and I get a -567. I multiply that number times 3. I get -1701. I multiply that number times 3, and I get a -5103. So those would be the next three numbers in the pattern. All right, next page. Example 3. Make and test a conjecture. All right, we're looking at numbers such as 1, 3, and 5, and they're called consecutive odd numbers. Consecutive meaning one right after the other, but odd because we're leaving out the evens. Make and test a conjecture about the sum of any 3 consecutive odd numbers. Okay, so we're just going to start out with the first 3. We've got the numbers 1 plus 3 plus 5. Okay, so I'm going to add those up and I will get 9. Now, 5 plus 7 plus 9, I get 21. See, these are the next 3. I start with 5, go 7, and 9. If I use 3, 5, and 7, those are my consecutive ones, I get 15. 7, 9, and 11 are consecutive odd. Add those up, I get 27. Okay, this is where we start looking for the pattern. Any 3 consecutive odd numbers, their sum is equal to the middle number times 3. The middle number is 3 times 3 is 9. Here the middle number is 7. 7 times 3 is 21. Here the middle number is 5. 5 times 3 is 15. Here the middle number is 9. 9 times 3 is 27. Okay, so then it says test your conjecture or your pattern. And you know, you can just keep doing this. You can take very large numbers and keep going with it. And let's go with something like 51 plus 53 plus 55. All right, so we've got 51 plus 53 plus 55. That adds up to 159. What is our middle number? 53 times 3. We get 159. When you do that enough and you check it at different levels, you can see if your conjecture is true. If you want to keep going and try to prove that false, go right ahead. Otherwise, we can make this conjecture and say that it is in fact true because there are no false examples. All right. Conjectures are only true if a counterexample doesn't exist. You cannot find a counterexample to prove this false, to prove this theory false. So because of that, I can say that my conjecture is true. It's only not true if you can find one counterexample. All right. So what we're going to say here to make our statement, make our conjecture is the sum of 3 consecutive numbers, and we should say odd numbers, equals the middle number times 3. Okay, now let's practice counterexamples, because some people will make a claim, and then you think about that claim or that conjecture and you'll say, hey, that's not true because in this situation it was false. That's what you would call a counterexample. It's proving that a conjecture is false. So if we've got the statement, the conjecture, the quotient of 2 whole numbers is a whole number, we want to find a situation where that is false. Okay, so your counterexample is proving it to be false. So find a counterexample Prove it to be false. All right. So quotient means to divide. So this is saying I can take any two whole numbers and divide them, and my answer would be a whole number. Well, if I were to take 12 and divide it by 5, I would get 2.4. This is not a whole number. So therefore, I've proven it false. This is what I would call my counter example. Okay? Your counter example is the statement that proves a conjecture to be false. The next one, the difference of any two numbers is always smaller than the larger number. Difference means to subtract. So I can subtract any two numbers, and my answer is always smaller than the larger number. In other words, than the larger number of the ones you used. Well, if I subtract -4 and -12, okay, I am subtracting a -4 and a -12. Well, we know that we can simplify that by adding. -4 plus 12 equals 8. Well, my larger number was -4. Okay, those were the numbers that started out. -4 was the larger number, but my answer is greater because my answer was 8. So I subtracted two numbers, but the answer that I got was greater than my larger number. Don't look at this plus 12 and say, wait a minute, no, you had 12. No, that was a -12. But when you subtract a negative, you actually end up adding. But I'm still subtracting two negative numbers there. Okay? So I've proven it false. So this is my counter example to this conjecture. Okay? Last one. The product of two numbers is always positive. Well, it doesn't say the product of two positive numbers or the product of two negative numbers. It just says the product of two numbers. So if I take a -5 and multiply it times a +4, those are two numbers, and I get a negative answer. Okay, negative answer. So therefore, this is my counter example. This conjecture is false. And that's it for 2.1.